I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to talk about residuals, standard error of the estimate, and R squared in a simple regression model. Let's start with an example. Suppose we have data on the yearly expenditures on advertising and the resulting sales for a sample of 8 companies in the same industry. Let's develop a regression model to predict sales by advertising dollars. In such a model, the sales would be the dependent variable, or the variable we're trying to predict, and the advertising dollars would be the independent variable, or the predictor. Let's look at our sample data. Our X variable are advertising dollars because we're going to try to predict sales by advertising, and these figures will be in millions of dollars. Our dependent variable, or the variable that we're trying to predict, are sales dollars. So one company spent $2 million on advertising and as a result realized $52 million in sales. Another company advertised for $15 million with the resulting sales of $165 million. Using the computer, we performed a regression analysis on these data, and the resulting regression equation is y hat equals 19.2742 plus 13.1183x. The y-intercept being the 19.2732 and 13.1183 is the slope of the regression equation. Is our regression model a good fit of the data? And how do we answer this? Let's start out by solving for what we call predicted values. Predicted values are solved for by putting the various values of x one at a time into the x variable here and solving for y hat. Since our first x value is x equal 2, we put that in the equation like this, and the resulting predicted value is 45.5108. Let's calculate the predicted value for our next value of x, which was 15. Putting 15 into the equation in place of x gives us a predicted value of 216.0484. Now we solve for all of the rest of the predicted values. So these are the resulting predicted values for all the various values of x. The two that we solve for x equal 2, the predicted value, and the predicted value for x equal 15. Well, why did we calculate predicted values, and exactly what are they? In order to have insight into what predicted values are, let's draw a scatter plot of our data. We have 2 and about 52, 15 and 165, 6 and 63. When the regression line is placed through the data, the predicted values are the actual values on the line that correspond with any certain given x. For example, when x is 6, the predicted value for 6 is 97. So here at the value x equals 6, the predicted value, or 97, would be on this line, and as would all other predicted values corresponding to the various x values. Predicted values can also be used to help us determine how well our model fits the data. By comparing the predicted values to the actual y values and determining the difference, we can see how much error the regression equation created in trying to predict the y variable. Let's go over here and subtract the predicted value from each actual y value. The difference between these two has a very special name, and it's called a residual, or an error in the regression model. So for example, in this first one, if we take 52 minus 45.5108, we obtain a value of plus 6.4892. So what this means is that the actual sales were almost $6.5 million more than what the model predicted. So let's do the next residual and see how it turned out. When we subtract 216 from 165, we obtain a residual of minus 51.0484. What this means is that the actual sales were $51 million below what the model predicted. Now let's compute the other residuals for this particular model. So how do we use residuals? Statisticians often study the various residuals to see if residuals or errors are large or small. And of course, small residuals are good because that means the model fit the data quite closely. Large residuals are not a good thing. It means that the model are missing the data a lot. Geometrically, we can look at residuals this way. If we have a regression line and we have some points off the line, for a particular value of x, we have a y value here, and associated with that same x, we have the predicted value here on the line. The difference between these 2 points is the residual, that is y minus y hat. So we can see that the residual is the vertical distance from the actual point to the regression line. The greater the distance, the more the regression line is missing the point, and the larger the residuals. While examining individual residuals, we gain insight into how well the regression model are fitting the data points. If we have a very large number of data points, like say 1,000 data points, the task can become daunting. So one of the things that might have occurred to us was, well, why don't we have an average residual that represents the residuals, thereby allowing us to look at one number? We would begin with summing the data. So if we sum the data, y minus y hat, what do we get? Well, it turns out if we sum these residuals, we will get a number that is virtually 0. As a matter of fact, it's a property of least squares regression analysis that the residuals will sum to 0. And if you remember our regression line placed through the points, you will see that some of the points are above the line and some are below the line. The equations for computing least squares analysis are such that the line fits itself geometrically, if you will, in the middle of the data, such that the residuals will add to 0. Because they add to 0, we're in a sense unable to compute an average because the average would be 0, but you can see that the average residual is not 0. So what do we do to overcome this property? Is to square the residuals, thereby producing all positive values. So for example, we take 6.4892 and we square it, thereby producing 42.1097. We square the residual minus 51.0484, and we get a squared residual of 2605.9391. We continue this process of squaring the residuals until we complete the column. So now we can total this column of squared residuals or squared errors, and as a result we get the following value. This equals the sum of the squared residuals. We give it a special name because it's a tool we widely use in regression. We often call it the sum of squares of error, and we often denote it as SSE or even SS sub E. As a standalone value, it's not used very widely, but it's used widely as a tool to help us calculate other statistics through which we can interpret the fit of our regression model.